Hey guys, and welcome. My name is Taylor Forbes, and I am going to be going through structural engineering and the AEC industry with Brian Covington. First, I'll start off by going through a little bit about the company we work for, Lynch Mykins. We're about 50 total staff members with 30 engineers, and we've been around for over 40 years. We're headquartered in Raleigh, North Carolina, and we have offices in both Virginia Beach and Richmond. We're certified in North Carolina as women-owned, which is great because that's pretty rare in our industry. What will we be going through today? First, we're going to go through what is structural engineering. Next, we're going to talk about how structural engineering fits into the AEC industry. Finally, we're going to talk about what we create together. What is structural engineering? Well, some days I feel like a physicist whenever I'm going through my calculations. Other days I feel like a magician whenever I'm making a structure stand up that looks pretty ridiculous. Some days when I'm writing my contracts and looking at the code, I feel like a lawyer. Other days when I'm working with architects to come up with a cool design, I feel like a designer. Some days I feel like a manager, making sure the project is progressing smoothly. But most days I would say that I feel like a kid playing with Legos. First things first, structural engineers are there to make sure that the building doesn't fall down. But we have a lot of other considerations that we have to think about whenever we're keeping the building standing. One of the first things we think about on a new project is what type of structural system that we're going to be choosing to work with. This is something that we pick with the architect depending on the project's needs. We'll go through a couple here. The first construction type that we have here is conventional steel framing. This is definitely one of my favorites and one of the more common types of construction. A fun fact about steel is that it's the most recycled material on the planet, more than all of their materials combined. Here we have a picture of what is called a pre-engineered metal building. It's pretty common for things like warehouses. Here we have what is called a composite beam. As you can see, there are some metal studs sticking up out of the metal deck. Below those metal studs are some structural steel beams. On top, they're going to pour some concrete. In our live demonstration, you'll get to see how composite beams act and where they get their strength from.
Hey guys, I'm Brian, and this is
Taylor.
And we're with Lynch, Mykins Structural Engineers, and we want to talk to you guys a little bit tonight about what structural engineering is. So when we talk about structural engineering, we're talking about the forces in a building, right? And how do we, as designers, account for those forces? How do we create the building in such a way that that building can withstand all the forces safely and keep everybody inside safe while they're doing their thing? So we have two types of forces that we work with primarily. One is gravity force, the other is lateral force. We're talking about lateral force, we're talking about wind, we're talking about tornadoes, talking about earthquakes, anything that's going to make the building want to go side to side. One of the most important parts of the building, though, is the gravity load resisting system. That's the system that you can apply your body weight to, or furniture to, or any kind of loading in the building that's going to be supported directly by the framing members. So, to illustrate this tonight, we've got a beam on the floor, right? We look inside a building, most of the stuff inside a building can be reduced to beams. And whether you look at it to the left or the right, top or bottom, it's pretty much all behaving the same way. So Taylor is going to step on our beam. What do you guys see? You should see it sagging. You should see it bending like this, right? So what's going on in that beam? We're going to draw it real quick here on the board so everybody can see. Here's our beam, right? Here are our supports. When Taylor stepped on it, she put a load right there in the middle of it, right? When she did that, the beam bent. It bent like this. Now, if I were to draw a line, a straight line, down the center of the original beam, that center line would be right here. When Taylor stood on that beam, that center line bent with the beam. So the new center line is right here. Now, because of that, what do you think is going on in the bottom half of this beam, right here? Are the fibers pushing against each other, or are they pulling away? The answer is they're pulling away. They want to do this. That's called tension, the tension force. When you have two members that are pulling away from each other, that's a tension force, right? And in this bent beam, we're creating tension in the bottom half. So we're going to put a big T right here for tension. At the top of the beam, are the fibers pulling away, or are they pushing against each other? The answer is they're pushing against each other. They want to press against each other. So that's called compression. We're going to put a big C right up here for compression, and two arrows to show that that's what's happening there. Now, In structural engineering, we have two primary materials that we most often use. Those are steel and concrete. Steel is very good in tension, and concrete is very good in compression. But the best system of all is a system that utilizes both. We call this composite action. In structural engineering, what we most often do is apply the steel where the tension force is, because the steel is better in tension, and the concrete where the compression force is, because the concrete is better in compression. So, what you'll often see, if I was to draw a line right here, and I was to cut this beam in half and look this way into that beam, what I would see would be a piece of steel, an I-beam. We call it wide flanges, but an I-beam, right? And then on the top of this beam, where I have the compression force, I have a concrete slab. Okay, and so to recap, we have the concrete slab up top, we have the I-beam or wide flange beam below, and then tying those two things together, we have a shear stud. This way, the steel beam and the concrete slab are gripped together as one unit. Again, compression up here in the concrete, tension down here in the steel, and the whole thing bends together when the loads are applied up here to the top of the beam. There's also another primary type of configuration that we see a lot in buildings, in reinforced concrete buildings, where we actually are going to put the steel in the concrete. So if this was a cross section of our beam right here, and the entire beam was concrete, we would put steel rebar reinforcing down here in the bottom. Again, the steel, which is the primary tension element, down here, right, where the fibers are pulling apart. Concrete up here in the primary compression region, where the fibers are pushing against each other. This way we make the most efficient use of both the concrete and the steel. And that's structural engineering in a nutshell.
Here we have our next structural system, concrete. Concrete's great for a couple of reasons. You can form it into a lot of different shapes. It's really good for floor vibrations, which we'll touch on in a second, and it also helps for fireproofing reasons. However, it is heavier than steel, so your foundations can get a little bit heavier and bigger. Just like with steel, where steel has conventional steel framing, composite steel framing, and open web joist steel framing, concrete has lots of different options as well. We can form it into, as you see here, one-way joist and beam systems, one-way slab and beam systems. Depending on the loading criteria and the column spacing, this can be an efficient option. Another structural concrete option is a flat slab. These systems are typically used when the columns are spaced a little bit closer together. Another concrete option is a two-way waffle slab. These are more commonly seen in older structures, so you may have seen these before. The previous concrete options mentioned are what is known as cast-in-place concrete, where the concrete is poured on the job site itself. There are other options where the precast can be poured before it gets out to site, known as a precast system. This tends to be a little bit quicker. Another construction material we have to choose from is wood. I can guarantee you that most of your houses are made out of this material. Typically, it's used in smaller buildings because of its ease of construction and ease of finding the material itself. It can be used for other small structures such as park buildings. More commonly, it's being used for architectural features and even in larger construction as mass timber. Another construction type is masonry. Masonry is actually referred to as concrete masonry units. So it is made out of concrete, but it's modular, so it goes up pretty quickly. I'm sure a lot of your schools are made out of masonry, and you can look around in the walls in your schools and see those blocks. Finally, we have cold-formed steel structure. This is different from the steel structure discussed earlier because this is known as light gauge. It's a lot lighter and less strong than the hot-rolled steel we talked about earlier. It's used in most conventional steel buildings as wall studs. So in your house, where you have wood stud walls, in a commercial building you would have cold-formed steel walls. However, this material can also be used as the load-bearing wall system in a conventional steel building. As we've gone through the different types of structural systems, I'm sure you've seen there are lots of considerations to take into account whenever picking a system. Some of those considerations are outlined below as building occupancy, loads and codes, site conditions, and serviceability. The First consideration is building occupancy. Is this building going to be used for a hospital or a school, or is it going to be used for an office? These things can help determine our structural system. Depending on what our building occupancy is, determines what loading criteria we have to use for our structure. That can be found in our codes that we reference. Our most common codes that we reference are ASCE 710, the International Building Code, and the North Carolina Building Code. Another consideration we look at is the site. What type of soils are located on the site? Are the soils good or bad? With the help of a geotechnical engineer, we can help determine our foundation loading requirements. Secondly, we look at where the site is located geographically. Is it located somewhere like Florida where there's really high hurricane winds? Or is it located somewhere like California where there's lots of earthquakes and seismic activity? Both wind and seismic play into our lateral load resisting system. There are lots of serviceability requirements, but we'll touch on vibrations and deflections. Have you ever been in a building with a long hallway and you ran down the hallway and felt the floor shake? That's an example of vibrations. We design our buildings to a level of vibrations so that people feel comfortable inside the building. For example, you don't want to locate a gym right beside a study room because then all of the floor vibrations will affect people trying to study. You also don't want to design beams to loose deflection criteria because if so, you might get cracks in your brick or your windows might look a little bit deformed. We'll touch on 4 more general considerations: money, number of stories, architectural constraints, and fire rating. Whether we like it or not, budget plays a big part in a lot of our projects. We have to think about balancing our design decisions with cost feasibility. How does number of stories play into our general considerations? For example, we wouldn't want to build a 20-story tower out of wood because it might not be as efficient as designing that building out of concrete or even steel. Architectural constraints. Where would the architect like our columns to be located? How does this play in with the architect's location of rooms? Where would the owner like the columns located? How tall is our floor-to-floor height? How deep can our structure be? These are all things that we have to communicate with the architect constantly so that we can work as a team to make the best building possible. And fire rating. Fire rating is determined by a number of things, but one of those can be the thickness of the structure. We have to work with the architect to make sure that all of their requirements for fire ratings are being met with our slab thickness or our structure thickness. Structural strength and serviceability. Strength is something that's required by the code, where serviceability is something that we just have to think about as structural engineers and problem solve. How is our structure going to impact the future user or the owner? As we mentioned before, vibrations play into a big part of that. Now that we've given you a big overview of structural engineering and what structural engineers do, how does all of that fit into this big AEC industry? You've seen lessons already on architecture, civil engineering, landscape architecture, and the list goes on. But where do structural engineers play into this? Typically speaking, structural engineers work on a team with mechanical engineers, electrical, plumbing engineers, civil engineers, underneath an architect. The architect works with the owner. Depending on the size of the project, there may be other consultants involved, such as lighting, roofing, or even safety. Like a structural engineer, they would work under the architect, and the architect works for the owner. Architects and their teammates work for the owner on the design side of the project, where contractors and their subcontractors work on the construction side for the owner. Again, this is for a typical project. As a structural engineer, we work with the architect through all of the phases, starting with schematic design all the way through construction administration. In schematic design, we're doing a lot of concept-only drawings. Then we progress into design development, where we start to add a couple more details and really get the design ideas fleshed out. Construction documents are the signed and sealed versions that we send to the contractor to build the drawings themselves. The construction administration phase is where we help answer any questions the contractor may have about our drawings. The key to making any project go smoothly is open communication throughout the entire project, whether that's us communicating with the architect, the other consultants, or the contractor, and sometimes even the owner themselves. What does the AEC industry create together? Our projects can be as large as an outlet mall, or they can be as small as a shelf. As a structural engineer in the AEC industry, we get to touch on a lot of really cool projects, from hospitals to schools, or even weird projects like zoo exhibits. There's never a dull moment. Every day is different, and we're constantly using our brains to solve really complex and cool problems. If you have any questions about structural engineering or anything that we went over today, Brian and I will be sticking around. There's no such thing as a dumb question. Thanks for listening.
The outline of the tiny house. What we're going to do today is we're going to talk through how the tiny house is framed. We're going to try to show you guys why it's framed the way that it is. So we're going to start with the roof. Generally, when we're laying out a building, we start at the top because that's where the load first gets applied. The load is then going to travel down through the building all the way to the foundation. But we're going to start up here. So when you think about the roof of a house, think about the load types that would be on that roof. You'll have, of course, the self-weight of the roof, but you'll also have things like snow in the wintertime, or perhaps the loads of you and I if we go up there to put a new roof on the house, or if some construction workers go up to put a new roof on the house. You'll also probably have things like pipes and insulation and ceiling fans maybe hanging from the roof itself. So we'll have a variety of dead loads during the lifespan of the building. Now, roof construction in homes is generally consists of two things. You have the rafters, which you'll see in these two cross sections as the dark red lines, right? And you'll also have plywood. Now the plywood is what spans between the rafters. And it's what the shingles get nailed to. You may have driven down the road before and seen a new roof going on a house, and you'll see the either plywood or OSB laid down on top of the rafters before the guys go up there and lay down the tar paper and shingles. So what we're looking at here is the floor plan like we talked about before. You see the 4 exterior walls of the tiny house. And so we're going to draw our rafters over this floor plan. Now what you can see here is how each of these rafters is spaced at about 2 feet on center, or 24 inches on center. This is about the maximum span that the plywood sheathing can handle. The rafters then span like beams. If you guys remember our example from the video, they span like beams between the two walls. And they carry the weight of the snow or the shingles or the people, whatever's on the roof. They carry that weight between the two walls. We've drawn 2 cross sections here below. The cross section on the left is what's called a shed roof. In this type of roof, you only have one slope. You can see the high side and the low side, right? The water, when it rains, drains down, obviously by gravity, to the low side and pours off, right? Now, the other typical type of roof is called a gable. And over here on the right, you see the typical gable framing. In this scenario, you have a high point in the middle, what's called the ridge, and then you have rafters on either side sloping down away from the ridge, so that when water falls on this, it drains off at each side evenly. What we've drawn in our roof framing plan is an example of a shed roof because we only have one line of rafters. In your activity, you can choose which one you'd like to draw. If you were to draw a gable end roof, you would have a ridge board running right down the middle, just like that. Okay, so next we're going to talk about the wall framing of the house. You have in these 2 cross sections that we've drawn studs on either side. And in actuality, studs are on all 4 sides of the house. These studs have to be able to do 2 things. They have to carry the weight of the roof down to the floor. They also have to resist wind pressure against the side of the house. These 2 things combine to determine for us the maximum spacing that the studs can be. When we talk about stud design, we're talking about compression generally on one face and tension on the other face. So it really resolves itself to beam action, again, similar to how we talked about in our video. Once we've determined the spacing of the studs, which again is typically 16 inches on center, we can then determine what type of sheathing, what type of wall sheathing we want to use for our walls. Usually about a 1/2 inch thick plywood is typical for your sheathing on your exterior walls. You're probably wondering to yourself, what about the holes in my walls? What about my windows and my doors? Well, this is an interesting scenario because we have weight coming down from the roof above, and we need to spread that weight out into the studs at each side in order to make room for our door. When we do this, we use what's called a header. A header is basically a small beam that runs across the opening of the door, spanning between stud packs at each end. This beam is sized for the total weight of all the rafters that land on it. In this picture here, we would size this beam for the weight of 2 rafters bearing on it. And then we would size our stud packs at each end for the number of studs required to carry that weight down to the floor below. In your activity, it's not necessary to determine how many studs. You can just put a pack there. Okay, so after this, we're going to move on down to the floor. Okay. Now again, it's similar to the roof in that each floor joist has to carry the load that's applied to it. So again, loads for your floor are going to be what? They're going to be you and me walking around, furniture, refrigerators, TVs, right? You could have dead loads from carpets and from floor finishes. There could be all kinds of things that would create load on your floor. Pets, for example. And what we're going to do is we're going to utilize, again, that beam action that we talked about to size joists that will span from one exterior wall to the next. Typically, these are going to be 2x8s or 2x10s in a tiny house construction, or in any house construction, really. If we go back to our previous slide, you guys will see at the bottom of each of these 2 cross sections, representation of the floor joist down here. So what we'd like for you guys to do is take a minute to work through your tiny house and lay out the framing of how it would go. Be sure that you catch each of your windows and doors and make sure that you put headers over each one of those. These are going to be typically double 2x10s or double 2x8s. One unique thing about your tiny house is that you have the option to put a loft level inside. If you were to say put your loft over your kitchen, you would need to design a floor system for that. So again, your floor joists of that floor would span from exterior wall to exterior wall and be sized to carry the load of whatever would be in that loft. Bedroom load is a little bit lower than typical floor design load, so maybe you could get away with using 2x6s for this. Your typical wall studs are going to be 2x4s, and the roof rafters for this could be 2x6s. So have some fun. Jump in there, draw some stuff, sketch a little bit, think about the ways that your tiny house would be framed. Hope you guys enjoy.